Hi everyone, welcome back. Today we're doing lowest common ancestor of a binary search tree. So we're given a binary search tree and we have to find the lowest common ancestor node of two given nodes in the binary search tree. And according to the definition of lowest common ancestor on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So in this case, 628047935, and we're given P equals to 2 and Q equals to 8. In this case, 6 is the lowest node over here that is the descendant of 2 and 8 over here. So it returns 6. And to our viewers that are new or relatively new to the concept of binary search trees are trees where each tree consists of nodes, and these nodes have up to 2 children on the left and on the right. The left children will be guaranteed to have a value that is less than the parent, and the right node is guaranteed to have a value more than the parent. So this property will be very useful as we tackle this problem. For the second one over here, for the same tree, we're given 2 and 4 instead. In this case, the lowest common ancestor is 2, as this lowest common ancestor over here contains both P and Q in itself or in its subtrees. So that's pretty much it. And for the final example, if you have 2 and 1, in this case, the lowest common ancestor would be 2, which is pretty much the root. So this example is pretty similar to the second, it's just that the third example is clearer. So the number of nodes in a tree is in the range 2 to 10 to the power of 5. So we are guaranteed to have at least 2 nodes in this case, which represents P and Q. And each node value would range from negative 10 to the power of 9 to 10 to the power of 9. All node values are unique, so we do not have to worry about situations where the parent has the same value as the left or the right node. P is not equals to Q, so there are 2 distinct tree nodes, and P and Q will exist in the binary search tree. So in this question, on the surface, it seems like as if we would have to use a depth first search, breadth first search in order traversal or whatnot. But actually, we do not need to do that because this is a binary search tree. So pretty much, if we check the root and we notice that the root is less than both the value in P and Q, then what this means is that perhaps we are better off checking the right side of the binary search tree, because both P and Q will be guaranteed to be on the right side of the root given the properties of binary search trees. Specifically, if a node is bigger than the root, then it's guaranteed to be on the right side of the root. So if the root is less than both P and Q, then P and Q is going to be on the right side anyway. So we can go downwards, and that right side node will be a lower common ancestor of P and Q. So that's the same for the inverse. If the root is more than P and Q, then P and Q would be on the left side of the root's subtrees. So we'll be doing an iteration like this. And once we hit to a point where the root's value is not less than both P and Q or more than P and Q, then we can take that current tree node as the lowest common ancestor of the binary search tree. So that's pretty much the approach that we'll be doing over here. That was a lot of words, so let's get started. So the first step will be to define a current pointer. So this current pointer would be pointing at a tree node, and this will be set to the root at the start. So the first condition is, let's define 2 functions, I guess, for more readability. Let's call this let's do it. Both P and Q in right subtree. So let's call this current pointer. This will be of type tree node, and this will return back a boolean. So we will do return current pointer dot val is, let's say, less than p dot val, and current pointer val less than q dot val. Yep, sounds about right. And we also do the same, both p and q in left subtree. And similarly, this would be taking in a tree node, and we will return us whether if the current pointer val is more than p val and current pointer dot val is more than q val. So if the current pointer is going to be more than both p and q, then both p and q will be on the left subtree. So go towards the left. So that's pretty much it. So we will use a while condition over here, and we will check for this. So while both p and q in right subtree current pointer, or both p and q in left subtree current pointer, then we will continue to take the current pointer and move it to the left or to the right. So if both p and q is in the right subtree, then we will set current pointer to be equals to current pointer dot right, else current pointer equals to current pointer dot left. So at this point, we will return current pointer because we need the tree node. So this is pretty much it actually. So let's quickly test this out with a sample test case. Let's use this approach over here. So luckily for us in this case, this is an iterative binary search tree approach. Typically binary search trees, in my experience, they are not really iterative in nature. You can technically define a depth first search or a breadth first search iteratively, but it's just nice to know that we do not have to do that this time. So in this case, we will start off from 6. Let's set the current pointer to be equals to tree node at 6. And we're looking for 2 and 8 over here. So now we hit this branch. In this case, current pointer dot val is 6 less than 2. Nope, that's not true. And 6 less than 8. Okay, in this case, this is true, but yeah, this is not true at all. So same for this. Let's do left subtree. Okay, 6 more than 2 and 6 more than 8. In this case, this is true, but this is false. But in summary, this while loop will never be executed, so we return the current pointer, which is 6. So this works for this test case over here. Let's try out with a second test case, p equals to 2 and q equals to 4. And similarly, we will start off with tree node equals to 6. So in this case, both p, so let's check here. Let's hit line 24 in a moment. So the current pointer value is now 6, and the p value in this case is 2. So 6 is not less than 2, and 6 is less than 8. So in this case, sorry, actually I confused myself, did I? Yes, q is 4. So 6 is not less than 2, and 6 is not less than 4. But 6 is more than 2 and 6 is more than 4. So it turns out that both p and q are in the left subtree. So since we will hit here, current pointer will now be pointing at yeah, let me just trace it here. Current pointer will now be pointing at 2. So we traverse current pointer to the left child, and now we are back at this while loop over here. So let's check. So is both p and q in right subtree? Let's see. 2 less than 2 and 2 less than 2 and 2 less than 4. Okay, in this case, you would actually, this will be false, fortunately, because 2 is not less than 2. So we will stick to this value over here. And similarly, in this case, 2 is not more than 2 and 2 is not more than 4. So in this case, this condition would be false, and this condition would be false. So yeah, looks great. So because of that, current pointer will be pointing at 3 node equals to 2, and that's the answer. So it looks like this works. So with that, let's run this against some sample test cases. This passes, and let's submit this solution. And this works. So in summary, let's quickly break down the time and space complexity. So in this case, every time we go down the tree, we are pretty much splitting the search space by half. So in the worst case scenario, it's possible that the binary search tree can be imbalanced. So in this case, the time complexity is OD, because we are pretty much going down level by level, and D in this case can be N. The D is the depth of the binary search tree, and N in this case is the number of nodes in the BST. So in the worst case, D equals to N when approximately N when binary search tree is imbalanced. So time complexity can be quite expensive. It can be OD. For the space in this case, fortunately for us, we do not use any variables that scales with respect to N or D. So the space complexity is O1. So in summary, for this question, we did some form of traversal. So we traverse left or right, but this is different from the typical depth first search or breadth first search for binary tree questions. We took advantage of the binary search property of a binary search tree to decide whether if we should go left or we should go right. And with that, I hope that this was a good practice for you. Subsequently, we will be touching another similar question, which is lowest common ancestor of binary tree, where we can't take advantage of the binary search property. But I will leave that to that other video to cover that. So with that, thank you so much for watching, and we will see you in the next one.